rubber inserts like this that fit inside brass holders, these brass holders, and you can imagine putting that inside here, threading the leaf through it, and then squeezing down on the thing to hopefully seal off any leaks. With this grass type, this is what we've used for sorghum and for maize, things like that. We used to make our own stoppers from RTV, I think they call it, this bluish rubbery stuff. And those fit in like this. So you can put this in, put your leaf through, put the other half in, stick it in.
So how big of a leaf are you doing? Like, are you just doing a portion of the leaf, or because if you're saying like
yeah, so
corn or sorghum leaf on
the bigger the better, I think. I mean, it depends on what you're interested in, of course. But for a sorghum leaf, yeah, or a maize leaf, yeah, they're not gonna. The way that I've used this is to take the leaf. What's this supposed to be? Right, that's the midrib here. And the problem is, you know, the maize leaf isn't flat, especially the midrib is a big thing. And so we would just cut that part off and leave this flat sticking through there, the flat part of the blade sticking out the top of the chamber, so that the midrib is below the stopper. Because one of the problems with this, as you can guess, is leaks. If you've got, you know, as you're increasing the pressure, if air is leaking out of this, not only does it sound like it's going to explode, but it doesn't give you as accurate measurement as you might like. So we would cut this off, and then you can fold this a little bit. Fold the leaf up in half or in thirds or something, and cram most of it in there with just the end sticking out a little bit.
What's the time frame from when you cut the leaf off to going to the pump and run?
You want to do it as quickly as possible, of course, but you've kind of got to go slowly, as I'll get into in a minute. And so, a minute, 2 minutes, something like that. You can do them fairly quickly. So it's a lot faster than the cyclometer. Yeah. And plus, the other advantage over a cyclometer is you can haul this out in the field with you and use it out there. So if you're interested in what the plants are doing, growing in there.
But then you also need to haul your nitrogen or
Yeah. But you don't need a big T cylinder, you know, you can use a smaller cylinder. In fact, this type of machine is, some of these are made to hold a little cylinder right in this bench, you know, one of those little steel cylinders. They don't hold as much gas, but they hold enough to make a lot of measurements. If you're inside, then you can use one of those big T cylinders. Ready? Yeah, so here's one. Here's one with the cylinder in place. But it's heavy, you know, it's really heavy. This is heavy enough without it, because it's made out of steel. Anyway, as I said, this was made by Precision Machine. There's really nothing to it. It's steel, it's some connectors, a gauge, and valve. It's not much to it. So they're not very expensive. Well, I haven't bought one. I've never bought one. But when this was made, it was like $500. That was a while ago. But it's not too pricey. It's way cheaper than a cyclometer. All right. Now, here's the key question. how does it work? Why is this? Why? Why? That's my question. Why? All right, remember way back when, talking about components of water potential, the pressure potential, this is just exactly the info that it had way back when. So the pressure potential represents effects of hydrostatic pressure exerted on the system. Can be positive or negative, can be zero. What does the pressure potential of zero mean? Usually that's taken to be the atmospheric pressure in the area that you're making your measurement. And that reference point we call pressure potential of zero. So for this leaf, where water is coming out of the xylem into the atmosphere, right? This is called guttation, and doesn't happen in all plants, happens in a few, and only at certain times, early in the morning. And what we can say then, when we see this, is that the pressure potential in the xylem of this leaf is greater than zero. It's positive. That causes the water in the xylem to go out into the atmosphere, right? Because it's moving, it's a convective flow, it's moving in response to pressure differences. Higher pressure here, lower pressure here, positive pressure here, zero here. So the water comes out. Right? So our reference point is atmospheric pressure. This is all from a while ago. Our reference point is atmospheric pressure. Now, let's consider a leaf inside this chamber when we're near the end point or at the end point. What are the components of water? Well, we know, neglecting gravity, we know that the total is the osmotic pressure. And if we keep, and this pressure is defined then as the pressure relative to atmospheric pressure. So if we keep these definitions the same, and we want to say, okay, what's the, for a cell here in the leaf mesophyll, what are the components of the total water potential for that cell when I've got some pressure here on the gauge? The components are, keeping these definitions the same, the total is the osmotic plus the pressure. But now we need an additional pressure component that represents how far above zero we are, this gauge pressure. That's what this P is. This gauge is telling us the pressure, it's supposed to be zero now, relative to atmospheric pressure. They call that the gauge pressure. Anyway, that's represented by this P. And so the total water potential of a cell here at the end point is the osmotic plus the pressure plus this additional pressure component, P. Right? These two aren't independent, but that doesn't matter for these purposes. Okay. Okay? This is the whole P. All right, now let's consider what happens when we make our measurements. All right. Let's assume we've got a plant growing outdoors somewhere under moderate conditions, right? So things are okay. The stomata are open, it's transpiring, the soil is moist. We come up to this plant and let's say we want to tell the total water potential of, that doesn't matter, of one of these leaves. Right? So we come up to it, and this leaf is transpiring. What we're going to do is sever the leaf, right? The total water potential in the xylem of the stem and this petiole is negative. If the plant is transpiring, total water potential is less than zero. The pressure potential is less than zero. There's a small osmotic component in the xylem. Not very big, but a little bit. But mostly that negative total water potential is due to a negative pressure potential in the xylem, a tension on that water in the xylem. So when we sever this leaf from the plant, what happens? That the stuff in the xylem here, as soon as it's cut, it has a pressure less than zero, less than the atmospheric pressure. So when it gets cut, the atmosphere pushes in on that, and the stuff in the xylem pulls back from that cut surface. Until and okay, so thinking, trying to think instantaneously, not easy. When that cut is made, the pressure potential in the xylem is close to what the pressure potential is in the cell walls of these mesophyll leaf cells. That's also a negative. In the cell wall space, the pressure potential is negative, and the total potential is negative. There's a little difference, because the water is moving that direction, but they're close to each other. So when we sever that leaf from the plant and the atmosphere pushes in, how far does it push in? It pushes in far enough so all of a sudden when it's cut, the water in the xylem has a pressure potential of 0. It's atmospheric. So that increased the total water potential. That, since water is incompressible, that step change in the pressure potential also happens in the cell walls of these mesophyll leaves, or mesophyll cells, leaf mesophyll cells. That causes a disequilibrium between the total water potential in the cell wall and the total water potential inside the cell. I assume they were more or less in equilibrium before. When we cut that, we increase the pressure potential. That increases the pressure potential outside the plasma membrane of these mesophyll cells. Now we've got, we've got a membrane, right? And can I remember this? And here, let me see. Before the cut, the total water potential out here in the wall and the total water potential in the cell are about equal. After the cut, the pressure potential out here increases, so now the total water potential inside the cell is less than the total water potential in the wall. It's a disequilibrium. And remember this equation for water movement across a membrane. If the reflection coefficient is 1, then with this movement goes according to the difference in the total water potential. So, right when the leaf is severed, this disequilibrium happens and water moves from the cell wall space into the cell, increasing its volume. That changes its water potential, and eventually enough water moves into those mesophyll cells so that now the water potentials become equal again. But the cells are a little bit bigger than they were before. There's less water in the xylem because the air pushed in there, and that amount of water went into puffing up all those cells in the mesophyll. They're a little bit bigger than they were before. They also have a different water potential than they had before. So we're not so interested in that. We're interested in this condition here before we made our cut. So we put our leaf in the chamber, screw everything down, increase the pressure. As we increase the pressure inside the chamber, we in effect squeeze those cells and squeeze the water out of those cells back into the xylem where it came from. And if we're careful in our measurement, we can squeeze those cells just enough to get the water in the xylem back to the cut surface. That's the condition that existed when we first cut it off the plant. And that is the water potential we're interested in, usually, when we make these measurements. So, my question now, okay, we've got things, if we hold the pressure constant at the end point so that water doesn't bubble out the end or something, my question then becomes, what are the components of the total water potential for the water near the cut end of the xylem and for the mesophyll cells in this leaf? If we hold the gauge pressure constant, we can come to a point where the water's right back to where it was when it was cut off the plant, and things are in equilibrium. The total water potential in the xylem now is the same as the total water potential in those mesophyll cells, because there's no movement of water anymore. We hold our pressure constant, we're not squeezing, we're not increasing the amount we're squeezing, everything comes into equilibrium. At least long enough to read a number off this gauge.
How long do you have to read that number? Like a second?
No, I mean, you can hold it there for a while, minutes if you want to. Yeah, it's not like, yeah, it's not like implying that it's crazy fast. You can, but you know, the longer you hold it, the more time you give for other things to happen that you don't want to happen, right? So you want to keep it short, but you know, easily a minute. So it's not, it's easy. It's easy to be able to read this number out. It's harder to tell when the stuff in the xylem is right at the point you want and not a little bit more or a little bit less, or yeah, that takes some tricks, and
So
usually
how do you-
use a magnifying glass to
Right.
watch that.
So how do you mean keep consistent, like for, if you're doing an experiment, does one person always have to do that reading stuff to keep
I mean,
it?
that would help, I would think, yeah, that would help. And a lot of times you can see a color change that happens, right? When the water starts getting close to that cut end, it'll turn a darker color, and then you can start to see it. And of course, it takes a few times of overpressuring it and seeing water bubble out the end and say, well, I went too far, and then doing it over again. But it's really not difficult to use this, and not difficult to read the gauge.
It almost sounds like a two-man job, one to watch the leaf and one to watch the leaf.
Yeah, although usually it's a one-person job, because you can, this valve, you can set it so that this increases slowly, and then you're just watching this. And as soon as you see that endpoint, then you glance over and make your reading. I mean, this is backwards. I'd be on this side if I was really using it. So.
I just want to imagine when it's something like that.
Yeah, well, you know, there are precautions to take. As I say, you know, you want to look at this from the side. Because people use this for small shoots, like small conifer shoots. And there have been cases where the whole shoot will pop out of the chamber and stick itself into the ceiling. So you don't want to have your face above it when that happens. It's better to look from the side. That's never happened to me, but I've never used it for conifer shoots. Better than the whole thing blowing Okay, so at the end point, my question, what are the components of water potential for this part of the xylem that's sticking out of the chamber? And what are the components of water potential for a typical cell inside this leaf? Because at the end point, as long as we hold the pressure constant, things will come to equilibrium, and those water potentials will be equal to each other. There's no movement of water in that system anymore. Equal water potential. So let's consider this cut end here. The xylem right out here. Well, in the xylem, the total is the osmotic and the pressure. Total water potential is the osmotic potential in the xylem. The pressure potential in the xylem, right here, is atmospheric pressure. It's outside the chamber, and so it's 0. So the total water potential in the xylem at this cut end is equal to the osmotic potential in the xylem, which is very close to 0. What about for a mesophyll cell here? Well, as I said before, the total potential is the osmotic plus the pressure plus this gauge pressure, this increase in pressure over atmospheric pressure. When we reach the end point, we hold the pressure constant, and those water potentials come into equilibrium. There's no movement between these cells and the xylem anymore, no movement of water. So these total potentials are the same. So, in the xylem, the total potential is equal to the mesophyll cell total potential. That's equilibrium, because remember, to move out of those cells into the xylem, we cross the membrane, and it's the total potential that's the driving force. So at equilibrium, those total potentials are the same. Here's the equation for the mesophyll cells. If we assume that the osmotic potential in the xylem, wherever it is here, is 0, then you can see that the negative of this pressure is equal to this, the total water potential in the mesophyll cell. Right? You see that? Oh. So this osmotic potential in the xylem equals, well, okay, pressure potential in the xylem plus the osmotic potential equals the pressure potential in the mesophyll cells plus the osmotic potential in the mesophyll plus this gauge pressure. The pressure potential in the xylem at the end point is 0. If we assume that this is also 0, then we've got 0 equals this plus or well, that's this. So this. That's how the pressure changes. How do you do it? I'll tell you what, think about it during class time on Thursday. That's all there is to it. It's really simple. So let me now talk about some things you have to be careful of when you use this thing. Pressure chambers are really, they're probably the most, if you're interested in what's happening in the field, pressure chamber is the most common instrument used for making water potential measurements. If your experiments or your treatments or whatever are amenable to lab work, then a thermocouple cycrometer or chilled mirror cycrometer would be a useful instrument too. But pressure chambers are used a lot for measuring water. But there's some precautions, so let's go through these. The first one I've already mentioned is leaks in the system. So here's a monocot leaf cross section. See, it's not flat. Typically the midrib, and you know this in maize, is a really big structure. And it's not flat. It won't go easily in between these two flat surfaces. You're gonna have a little bit of a gap on one side or the other, or both. And your gas, your compressed gas can leak out there. Usually it makes a really big noise, you can hear it, and say, oh my goodness, what's happening? So you have to try to minimize that. Again, for a petiole of the dicot leaf, they're not perfectly round either. And so you can get little leaks in that arrangement too. And so one thing that really helps is to use this high vacuum grease. It's really thick grease. They take it out of here, but there's a reason it's in this dry. There's a reason all this other stuff is kind of greasy, because it really works. It stops those kinds of small leaks. Stopcock grease, you can use stopcock grease, but it's not as thick as this, what's called high vacuum grease. And it really does help stop those leaks, those small leaks. So that's a good deal, or a good way a good precaution to take is for the part of the leaf that goes through the stopper, either the flat stopper or the round stopper, to coat it with some high vacuum grease. It makes a mess, but it works. Okay, that's all I have. Okay. Let's see. The biggest problem, though, then becomes if you can stop the leaks, which that's not a hard problem. The biggest problem is water loss from your sample, from the time it's excised from the plant until the time you reach the end point. So the first, there's a one-to-one correspondence between water content and water potential. If your sample loses water, it's going to change its water potential. And that's not what presumably you're interested in the water potential that was there when you cut the leaf off the plant. Okay, here's an article from Ag Meteorology that demonstrates this. Bias in pressure chamber measurements of leaf water potential. Okay, so they had some barley plants growing out in the field, and what these people did was to take a pressure chamber out in the field, cut the leaf off the barley plant, stick it in here, make a reading of the water potential. The quickest they could do it was 30 seconds. That was when everything was going fine. The quickest they could make a measurement was 30 seconds. All right. And here's the data they got from making it quickly, these open circles here. Just putting the leaf in the chamber by itself. Okay, well, that was okay. But what they did next was they covered it with a bag. I think, I don't know what kind of a bag, some kind of a bag. And they were able to stop this decrease in water potential over time that they saw when they didn't put it in a bag in the chamber. And they got this data. Right? Then they put it in a moist bag. I don't know how they moisten it. Sometimes you can moisten it by breathing, like in a plastic bag. You breathe in there and get it humid, put it in there, or put a moist paper towel in the bag or something, and put it in there. And in that case, they got this data set where the water potential actually increased with time in this humid bag from their initial reading. But then they got the better idea of, let's use cling film, right? The plastic wrap, saran wrap, or glad wrap, or whatever brand you like. And they covered their leaf up before it was cut off the plant. Then they cut it off the land. And when they did that, it didn't matter if it was bagged or unbagged. They got the same looking set of data, which are the filled circles on the top. Now they can interpret their first technique here of just measuring it within 30 seconds. Even when they did that, they figured they already lost 0.6 of a megapascal just because of the water loss from that leaf before they could reach the endpoint. But by covering up with plastic, they were able to get consistent measurements. Yeah, this, I should have said this before. This x-axis is the time that they took to reach their reading, or the time since it had been separate from the plant. So 30 seconds was as quick as they could do it, and already they were 0.6 megapascals more negative than they would have been if they had stopped transpiration from the leaf. It's sure.
If you left like the bag on, when you put it in there, it wouldn't affect anything, would it?
Well, if it was humid, when it was humid, this leaf absorbed some of that, if it wasn't wrapped with plastic. But if it was wrapped in plastic in a human bag, then it didn't increase its potential, because presumably that water from the air can't get through the plastic back to the leaf.
Like if you dipped in like a turf or wax or something like that, would that start ruining some stuff?
That would stop the water loss, that's for sure, but it might screw up the leaf, you know. To be able to dip it in paraffin, it's gotta be pretty hot, and I think that might screw up the, whatever. But, yeah, maybe you could spray something on it.
Liquid Band-Aid.
Liquid Band-Aid, maybe, it might work. Sure, maybe. Anyway, it's important to be aware of this, because here's a data set from this group of barley plants, I think it was. Oh, it's wheat or barley, well, whatever. Where they went out from sunrise to sunset and measured water potentials with a pressure chamber. And for example, if you just have a leaf uncovered, not in a bag, uncovered, you get this data set here where water potential is close to 0 before sunrise, come to a minimum midday sometime, and then they increase after sunset, eventually wind up back where they were. So without any of these other data points on here, that looks like a reasonable time course of water potential. You know, how would you know that wasn't correct? But